Hello, in this session we'll look at general form of conservation law. So what does it means and what is a mathematical expression for that? So if you look at etymology of the word conservation, it states it has something called as prefix con, which means with or together, and the postfix has a root servere, which means both are Latin, to keep or to guard, or let me recorrect this, guard or to observe. So if we want to write down literally, it means in physics to maintain a quantity constant during a process of change. So this is what is etymological meaning of the word conservation is. Now what we are told in physics in general terms, a quantity is said to be conserved if it can be neither created nor destroyed. So this is what we were told, a quantity which is neither created and nor destroyed. So it belongs from the basic idea of philosophy, that idea from philosophy. There are no specific roots, but according to philosophy, there is a concept called as nothing comes from nothing. So it means what exists now has always existed. So that's the typical philosophy, and this is what conservation means. So it came from Greek philosopher Parmenides. Though it is titled to Greek philosopher, but can be found easily in Indian literature, can be found in Indian mythological texts. The modern concept of this conservation actually was introduced mathematically by Amy Noether in 1915. So let me change this. In 1915, she was a German mathematician. German mathematician. She published the work in 26th July 1918. 1918, 26th July. At Royal Society of Sciences. Society of Sciences in Göttingen in Germany. So according to her theorem, she tried to connect the physics and symmetry. So according to Noether's theorem, which is popularly known, so it states that for every symmetry exhibited by a system, there is a corresponding observable quantity that is conserved. So this is what the theorem states. So it relates symmetry to the quantities which are conserved. So that is the first definition of conservation. Entities, according to physics, that can be conserved are, we know them very well according to fluid mechanics, are mass, momentum and energy. Also electric charge can be conserved, and this is not related to mechanical engineering, but cash can be conserved according to economists. So first three entities, especially mass, momentum and energy, these are always studied in mechanical engineering. So our focus in this session will be on these three quantities. So if we try to again restate the Noether's theorem, so according to Noether's theorem, the momentum, which is linear momentum, can be stated. The laws of physics are same regardless of where we are in space. So this is basically symmetry, which we say as position, based on position. So positional symmetry implies linear momentum which is conserved. So it implies linear momentum is conserved. So this is always true. Whenever we have positional symmetry, we say it's a linear momentum which is conserved. Similarly, angular momentum, which states again laws of physics are same if we rotate if we rotate about an axis. So this actually is talking about rotational symmetry, so which implies angular momentum which is conserved. Angular momentum which is conserved. Okay. So now we have energy. So it states now again that laws of physics are same and they do not depend on what time it is. So that is basically a temporal symmetry, what we can say. So temporal symmetry implies energy is conserved, implies energy is conserved. Sorry, let me recorrect this. Energy is conserved. So in short, actually let us look at these statements. According to linear momentum, positional symmetry, which is causing conservation of linear momentum, and rotational symmetry implies angular momentum which is conserved. Similarly, temporal symmetry conserves energy. So that was the formulation by M. E. Noether. There is also an electric charge conservation part. So it states that interaction of charged particles with an electromagnetic field remains same when multiply fields by a complex number e to the power I phi. Phi is electrostatic potential in this case, so which signifies symmetry in magnetic fields. Okay, so that is what it is according to Noether's theorem. So in general, in physics, we know that entities can be first of all tensor, which are of higher definition and higher dimension, higher order entities. They can be vector, can also be stated as first order tensors, and scalar, which are said to be zeroth order tensor. So mass and energy are scalar, as we know from physics, and momentum, which is a product of mass and velocity, is a vector. So scalar and vector, these are two forms of conservable quantities, so accordingly we have to make the statement. So the generalized form of statement of conservation is it states that the variation of total amount of a quantity phi in a domain is equal to balance between amount of quantity entering and leaving the domain plus contributions from eventual sources generating that quantity. So this is what it says: the variation of total amount of quantity phi in a domain is equal to balance between amount of quantity entering and leaving the domain plus contributions from eventual sources generating that quantity. So let us change the colors of these parts of the statement so that we can formulate the terms accordingly. So these are three terms, if you see, and we have divided the statement into three terms. So let us write down now scalar conservation law by using those three parts. So let us consider an arbitrarily shaped control volume, what we can say, as a domain, what we have stated in above. So let phi be any scalar quantity which can be usually a flow property, and this quantity is per unit volume because it is situated within a control volume. That our volume we are going to denote by omega, which we are saying as control volume, and it is of arbitrarily shaped intentionally, so we can devise the generalized formulation, and this is fixed in space. So what we actually trying to model is something called as Eulerian frame of reference from physics and integral approach for modeling mathematical equations from mathematics. So this is Eulerian integral approach. Okay, let S, capital S, be closed surface, can be called as control surface. Now let us consider a small control volume within this actual given domain. So let us call this volume by d omega. So consider a small control volume d omega. Now there is a property change within this, so the property stored in this will be the flow property inside small control volume will be inside small control volume is phi, property phi times d omega, because phi is property per unit volume, so multiplied by small volume d omega. So let us call this as term number 1. Now based on this we can devise the total change. So according to this statement, the first part states that total amount of quantity in a domain. So right now we have just formulated a quantity within a small domain. So total amount of quantity in a domain will be integral form of that. So volumetric integral omega integral phi d omega, which is equivalent to in our Cartesian frame as xyz, so which is a triple integral of phi dx dy dz. So kindly note this. So hereafter we will be using omega integral, which means triple integral. So again, then there is a part called as the variation. Now variation of this part, that is term 2, will be variation of term 2. It's a time variation, so that's why d dt, partial over partial t of omega integral of phi d omega. Let us call this as term 3. So that completes the formulation of first part of conservation statement, variation of total amount of quantity phi in a domain. Now next term is amount of quantity entering and leaving. So for this, now let us consider some quantity which is coming in a control volume. So let us call this by letter f bar. It will have some direction, so that's why f bar, and it will come from some small area. We'll call that as ds. Now this ds will have normal directed outward, denoted by n cap. So the quantity which is coming in will be like this, and it will be a bar dot ds bar. Okay, so this is along normal direction, so f bar dot n ds actually is equivalent to f bar dot ds bar, so we need to note this. So it's a scalar product, we need to note, because the outcome has to be, the final product has to be scalar. Okay, so the next term according to our statement of conservation is amount crossing the domain, amount of flow property crossing domain. And in general, usually such terms, that is the amount of phi, which is a property, flow property, amount of phi crossing unit surface, crossing unit surface, crossing per unit surface per unit of time is called as flux. Per unit of time is, the quantity is usually indicated by the term flux. So now for this case, in the given situation, normal component here, the normal component which is of interest to us, because all our other the components which are tangential won't come into the domain, so only normal component is responsible for entering the quantity inside it, and that is fn ds is equals to f bar dot ds bar. Let us call this as fourth term. So usually in geometry we are told, like in geometry the surface normal is positive when pointing outwards. Normal is positive outwards, and in this case flux is coming inwards. So therefore we have to negate this expression by net total contribution flux, which is entering and leaving as well, negative sign, so that flux entering will be a negative and flux leaving term will be a positive. So mark it with a negative sign. So here also we need to note that the closed surface integral f bar dot ds bar is actually double integration in Cartesian frame such as xy f bar dot dx dy. So this is what we need to note. So then last term, which is third term according to our statement, is, so let us go back to the statement, and it states that plus contributions from eventual sources. So sources generating that quantity. So we need to talk about now the sources which are going to be responsible for generation of quantity. So sources usually are of two kinds. First one, a volumetric q omega, volumetric source, volumetric sources. So let us try to indicate them. So they will be throughout within this control volume, so which will be generating that property q omega. So this term will be omega integral of, so that is volumetric integral of q omega. So q omega d omega. Again we need to note this is equivalent to volumetric integral, which is dx dy dz. Okay, so let us try to change this style to the expression or the statement part. Now second source will be surface source of flow property. So that is generation of the property from surfaces. So again we need to indicate some small component of ds, and the sources, the generation of that quantity, marking as qs bar, because it is going to be throughout the surface. So naturally it has to be vectorial, it will have some direction along with it. So this part can be rewritten as the surface closed surface integral of qs bar dot ds bar. So let us call this as the earlier term as 7th term and this as 8th term. So now net contribution from sources will be addition of these two terms. Sources is volumetric integral of q omega d omega plus closed surface integral of qs bar ds dot ds bar, which is a scalar product. So 9 term. Now we need to just put all the terms together. So according to our statement, final form of statement from terms. So let us identify them. So we need this third, 5 and 9, 3, 5 and 9. So let us copy them as they were. Okay, so third term is this, which is a time rate of variation of the quantity within a domain, and is equals to the amount quantity entering and leaving, which is this term, plus contributions from the eventual sources generating that quantity. So these are sources. Okay, so that is a form, integral form. So let us try to put all the equations in one line, all the terms, sorry. Okay, so this is a final form, and let us write down this as equation number 10. So this equation 10 is called integral conservation form. Integral conservation form. It is also known as Reynolds transport theorem. In short, RTT, Reynolds transport theorem, RTT. So which is named after scientist Osborne Reynolds because of his work in 1842 to 1912. So this equation is in integral form, which is equation number 10. So this equation can also be converted into differential form, can be converted into differential form using an identity from calculus, from form by using some identity from calculus, which is known as Gauss divergence theorem. Though it is titled by the name Gauss, but actually firstly it was stated and invented in 1762 by Joseph Louis Lagrange. Italian mathematician. Also in 1813 it was stated by Carl Friedrich Gauss, German mathematician. So the first proof of this was given in 1826 by Mikhail Vasilievich Ostrogard, Russian mathematician, Russian mathematician, who gave the first proof of general theorem, Ostrogradsky. Okay, so also it was invented in 1824 by Simeon Denis Poisson, the same person by which Poisson equation and Poisson's ratio in solid mechanics are named, in 1822 by George Green. That's why known as Green's theorem, British mathematician theorem. In 1822 by Pierre Frederic Sarus, French mathematician. So last three are actually Gauss theorem, what they say. So this states that surface integral f bar dot ds bar is omega integral of del bar dot f bar d omega. So let us correct this del bar. Okay, so we all know the operator del bar, which is partial over partial x I cap plus partial over partial y j cap plus partial over partial k z k cap. So let us call this as 11. Now we need to substitute this form of theorem and this equation 11 in equation 10, because the last term is also surface integral, so we need to change it to omega d dt omega phi d omega plus omega integral of del bar f bar d omega is equals to omega integral of q omega d omega source term plus omega del bar dot qs bar d omega. So let us call this as 12. Now if the shape of this domain, shape of control volume, which is a domain, is constant, is always going to remain constant with respect to time t, so it won't change. So that's why we can comfortably take the d dt term inside. So it will be d phi dt of d omega plus omega of del bar dot f bar d omega plus q omega plus volume integral of del bar dot qs bar. That is called 13. So now we can use the concept such as whatever is applicable to control volume must be applicable to a small element. So whatever is applicable to control volume or a domain must be applicable for a small element within the domain or control volume. That is when, or otherwise we can say when control volume shrinks to a small element, so it get reduced in all the dimensions. It is like all dimensions dx dy dz are tending towards 0, so it gives d phi partial phi over partial t plus del bar dot f bar is equals to q omega plus del bar dot qs bar. So we can rearrange this equation 14. So all the vectorial products calculus term will be on one side, so del bar dot f bar minus qs bar, and that is equals to q omega. So let us call this as 15th. So this is a differential form of the conservation equation. So we have obtained this f bar, actually we have indicated as flux term. Now this term will have two components. The first part is convective flux, and then its second is diffusive flux. So let us call them fc and fd bars because they are vectors. So fc bar is convective flux. So again, if we look at the word convective, so before modeling we need to understand this, what is meaning of convective flux. So etymological idea, if you look for this, so again it has the same prefix, which is a Latin con, so which we have already used in the word conservation. So if you recollect, so which means with, conservation with, which means with or together. So same root here also it has. it means with or together. And there is the postfix, which is a verb, Latin verb, where. It means to carry. It means to carry. So literally, conveyere, which is the Latin word of convective, conveyere, it means to bring together. So this is like bringing all the fluid properties together which we have considered. So bring property together, that what it means. There is another term which is advective flux, commonly used in especially chemical engineering branch. So here again I want to mention the etymology. Ad means to or towards, so there is slight difference in between advective flux and convective flux. So advective flux, which has a root advere, means to carry property towards something, so wherever species difference is, so you need to note this down, that it is to carry towards, and convection means to carry together. So advection is more like directed. There is next term which is diffusive flux, FD bar. So again, etymology, if we look at this, it has a Latin root which is diffundere. So it means to spread or to extend. So which is, the first property means to carry together, and this means to spread out. So the mathematical formulations of these quantities will be, so we are carrying something, so naturally with some velocity it will come, so property multiplied by its velocity component, so velocity of flow we can say. So that defines the convective flux. So let us title this term as equation 16. Then diffusion term especially we can obtain from fixed law of diffusion, which is similar to Fourier's law of conduction. The only difference being there it is talking about temperature and here it is talking about mass diffusion. So it was defined in 1855 by Adolf Fick, German physician. So it states that basically the diffusion flux is directly proportional to coefficient of diffusion density difference and the term phi, so gradient of this phi. Phi actually means quantity per unit of mass, per unit of mass, and alpha here means diffusion coefficient or mass diffusivity, as if like in Fourier's law it was conductivity, here it is diffusivity. So rho is density, density of fluid. And now we can substitute these terms. Let us call this term as 17. So we can substitute 16, 17 in, let us look at the form, which is either we can go for 15 also, or the integral form which we need to look is the original form. Okay, this one, equation 10. So in equation 10. Okay, so the formulation is partial over partial t of omega integral phi d omega plus So now we need to substitute this convective flux. So surface integral of convective flux, which is phi v bar dot ds bar, is equals to surface integral of diffusive flux. So we have taken this term on the other side to avoid negative sign, okay, plus the sources term, which were q omega d omega, and the surface sources closed surface integral of qs bar dot ds bar. So let us call this as 18. Okay, similarly we can substitute 16 and 17 in differential equation, which is I guess 15, yes. And we can little bit rearrange that. So partial over partial t of phi plus del bar dot phi v bar is equals to del bar, now diffusion coefficient, so that is alpha rho d phi del bar phi plus q omega plus del bar dot qs bar. So this is equation 19. Now these equations 18 and 19 are called convection diffusion equation. Convection diffusion equation in integral and differential form respectively. So in every CFD code, these equations are solved. So they are basic governing equations of conservation of mass, momentum and energy, convection diffusion form of equation. So let us write down now the second part, which we have is conservation equation in vector form. So when flow property itself is vector, the flux of that property will be tensor. So we need to note this. So this we are trying to indicate by f and 2 bars on the head. So our old equation, we can simply use this equation, which is we have already reduced, equation number 10, which is integral form of conservation statement. So we can substitute there. F double bar can be rewritten as, so partial over partial t of now q bar, which is a vectorial, so phi bar, sorry, term, and surface closed surface integral of fs double bar dot ds bar. Now this product is again a tensor product, so that it will deduce the terms which are vector. So again tensor product, and let us call this as 20. So again, by applying Gauss divergence theorem, we can deduce into differential form. So we can write ddt of omega integral phi d omega plus omega integral of del bar dot f bar d omega is equals to omega q omega bar d omega plus omega integral of del bar dot qs double bar d omega. So this is 21. So again, this control volume, the considered domain, can be shrinked to small differential element. So small element of differentials is, that is tending dx dy dz towards 0. So we can write partial phi bar over partial t plus del bar f double bar, which is tensorial quantity qs double bar, is equals to q omega, which is 22, where now this flux component will have again two contributions, convective and diffusive flux. So all are tensorial. So this convective flux, which is of tensor, can be written as tensor product V bar. So remember, this circle cross is symbol of tensor product. Okay, so let us call this as 24th. And similarly, diffusive flux can also be written as negative alpha rho d phi bar and dx. So now these terms, this gradient will be tensorial term. Okay, so in indical notations which were introduced by Einstein, we can write down Fc, Ij, which are indices, so phi I and Vj. Similarly, diffusive flux Ij can be written as negative alpha partial over partial phi I and xj. So let us call this as 25, 26 and 27. So these are now in vector form. So now we can apply this form to conservation of mass, momentum and energy. So they are templates like